Today, we're diving into something that literally defies logic: ultra-large crude carriers. I mean, we're talking about floating engineering marvels that carry mind-boggling amounts of liquid across the world's most treacherous oceans. So how do they not just snap in half or sink? How do you even safely handle millions of gallons of sloshing cargo? Well, today we are going to completely demystify these leviathans. We're going to break down the wild physics, the ingenious environmental safeguards, and the incredibly precise logistics that make the whole shebang work.
So here's our roadmap for today. First, we'll look at the giants of the sea. Second, the anatomy of a tanker. Third, stabilizing the ship. Fourth, environmental protection design. And finally, the loading process. Let's get right to it.
Section 1. Giants of the Sea. And really understanding the sheer scale of these things.
Right off the bat, we need to make a massive distinction between the two main types of oil-carrying ships out there. You've got your product tankers. These are the smaller ones that move refined stuff like gasoline or jet fuel right to consumer markets. But crude tankers? Oh man, these are the absolute giants. Their whole job is moving massive, raw quantities of unrefined crude oil from where it's pumped out of the ground all the way to the refineries. And today, we are zeroing in on the biggest of the big, the ultra-large crude carrier.
Moving on to Section 2. Anatomy of a tanker. The exterior view. Seriously, if you look down at the deck of an ultra-large crude carrier, it's like looking at a floating industrial city. You've got a helicopter landing pad, these massive cranes for lugging heavy equipment around, an entire accommodation area where the crew actually lives and sleeps, plus the control room and your emergency escape boats. But check out this one absolutely critical safety feature: the mast risers. These are piped straight down to the cargo tanks deep below deck. Why? Because when you're pumping millions of gallons of oil in or out, the pressure buildup is insane. Those mast risers are literally venting that pressure into the air. Without them, yeah, the ship's structural integrity would be toast.
30. That's the number. When you picture a vessel that's literally several football fields long, you'd probably expect a crew of hundreds, right? Nope. Thanks to incredibly advanced automation, crazy efficient design, and that centralized control room we just talked about, the entire crew running this behemoth is usually only about 30 people. It's just a huge testament to how dialed in the engineering really is.
Okay, Section 3. Stabilizing the ship. Let's look at the physics inside the hull.
Okay, imagine for a second you're carrying a wide, shallow bowl filled right to the brim with water across your living room. You take a sudden step, the water violently sloshes to one side, and suddenly you're completely off balance. Now, take that exact scenario and scale it up to millions of gallons of thick, heavy crude oil out in a rough, churning ocean. Seriously, what happens if a giant tank of oil sloshes entirely to one side of the ship right as a massive wave hits?
Well, the answer is a frankly terrifying physics problem called the free surface effect. This kicks in when a huge amount of liquid inside a single giant tank gets moving side to side. As it shifts, it builds up massive kinetic energy that just slams into the inside of the ship's hull. If an oil tanker was basically just one giant hollow bathtub full of oil, that liquid rushing to one side would hit with so much force it could literally flip the entire ship over. No joke.
But engineers are smart. Their solution to the free surface effect is actually pretty simple but brilliant. Instead of one giant cavernous holding tank, they use multiple smaller oil cargo tanks. By chopping the hull up into smaller compartments, you completely break up that liquid's momentum. So when the ship rolls in rough seas, the oil's impact is chopped into smaller, separate punches rather than one giant knockout blow. It drastically cuts down the force on any one side of the hull, giving the vessel the stability it desperately needs to stay upright.
Which brings us to Section 4, Environmental Protection Design.
Here's a crucial fact. Today, all oil tankers over 120 meters long are legally required to have a double hull. Now, why is that? Well, back in the day with older single-hull ships, if they ran aground or scraped a reef, the hull would tear and bam, immediate oil spill into the ocean. Just an absolute environmental nightmare. A double hull completely changes the game by acting as a built-in failsafe. It's a physical buffer. So if the outer hull gets shredded, the inner hull stays perfectly intact, keeping the oil safely inside where it belongs.
But wait, having a double hull means you got all this empty space between the two layers, and engineers actually put that to work. See, an empty oil tanker, like right after it drops off its cargo, is dangerously unstable. It doesn't have the weight to fight its own buoyancy, meaning it sits way too high in the water and just gets tossed around by the waves like a cork. So the solution? They use that gap between the hulls as water ballast tanks. They pump in heavy seawater to weigh the empty ship down and keep it stable for the trip home. However, that solves one problem and creates another. When you suck up seawater in one part of the world and dump it out halfway across the globe, you're accidentally transporting invasive microorganisms that can absolutely devastate local marine ecosystems. So, to fix that, every ship has a mandatory onboard water treatment system. Before a single drop of that ballast water goes back into the ocean, it's rigorously treated to kill off any harmful bacteria.
Now, aside from all that crude oil, these ships hold a bunch of other liquids below deck too. We're talking heavy fuel oil to power the engines, a sludge tank for waste, and fresh drinking water for the crew. So think about it. What happens if a shared wall between the heavy engine fuel and the fresh drinking water develops a crack? Total disaster, right? To stop that from ever happening, they use something called a cofferdam. It's basically just an intentionally empty space separating tanks that hold different liquids. That way, if a tank wall cracks, the fluid just leaks harmlessly into the empty cofferdam instead of contaminating the tank next door. Plus, it gives the crew a safe, dry space to actually climb in and weld the leak shut. Pretty clever.
Okay, our final section, Section 5, the loading process, a delicate balance. Now, if you peeked into the pump room of one of these carriers, you'd probably just see a chaotic, confusing jungle of pipes. But the loading path is actually highly controlled. It's totally linear. First, the oil enters from the outside through a massive connection point called the manifold. Then these heavy-duty pumps kick in, forcing that super heavy liquid deep down into the belly of the ship. Finally, it pours into the cargo tanks through this wide opening called a bellmouth. And get this, it doesn't spray down from the ceiling. It actually fills from the very bottom up. This prevents crazy splashing and, more importantly, cuts down on static electricity, which is obviously a huge fire hazard.
And when you're loading a ship of this scale, weight distribution is literally a matter of life and death. If you just pumped all the oil into the front of the ship first, the crazy weight would literally snap the vessel in half or cause it to lose balance entirely. The weight has to be even across the board. So let's look at a quick example, say a ship with 15 cargo tanks. They don't just use one pipe to fill them front to back. They use a section system. Pipeline A will handle only the first 5 tanks. Pipeline B takes the middle 5, and Pipeline C handles the back 5. Because it's hardwired this way, it actually doesn't matter which pipeline gets turned on first. The weight naturally balances itself out across the entire length of the ship. No fatal imbalances, just smooth sailing.
Let's wrap things up with a few more quick operational details, just to show you how wild the logistics really are here. First off, raw crude oil is thick, like incredibly viscous. It really doesn't want to flow. So the cargo tanks actually have heating coils built in to warm the oil up, making it thinner and way easier for the pumps to handle. Second, these ships are way too huge to ever pull up to a normal, shallow dock. So they load up offshore. They use these massive loading arms and buoys out in deep water that hook directly into subsea pipelines. And finally, when it's time to unload at the destination, if the dock is still too small, they do something called lightering. They essentially park out at sea and safely transfer the oil into a fleet of smaller tankers, which then ferry it the rest of the way to the shore.
It's honestly amazing when you step back and look at the whole picture. These colossal vessels aren't just giant floating buckets of oil. They are actively balancing high-stakes physics, rigorous environmental protections, and incredibly complex global logistics every single second they're out on the water. From the mast risers and cofferdams to double hulls and ballast water treatment, the sheer amount of problem-solving happening at any given moment is just staggering. So the next time you look out at the horizon and spot a massive ship slowly crawling across the ocean, ask yourself, what other invisible engineering marvels are hiding just beneath the surface? Thanks for hanging out with me for this explainer, and keep learning.